do quiz online, that is replaced with your Chapter 1 and Chapter 2 quizzes. Okay, so we're not doing that in class. You're doing those outside of class. Now we have 9 different objectives for today. Okay, only one of those, number 9, is really new. So we're just going to go through all of them. All right, here's your vocab. Really quick, it says the arithmetic mean of a variable is computed by adding up all the values of the variable in the data set and dividing by the number of observations. Guys, it's just the average. Okay? The population arithmetic mean, i.e. population average, is given by mu. The sample is given by x bar. And again, this is just how they write this. They're saying add up all the data points and divide by the total number of people in the population. Okay? So that is your average. The next thing we want to talk about is the mode. It's the number that occurs the most in your data. You can have unimodal data, so data that shows up maybe in this class, your age, the number that shows up the most is 17. Okay? Or maybe we have 15 people in here with 17 and 15 people in here are 18, and then everybody, all the other ages are less, so then it's bimodal. Whatever number shows up the most is the mode. You can have bimodal, trimodal, if you have ties. Okay? The median is the number in the middle that lies in the middle of the data. And there are some steps for finding the median, which we'll go through. This is out of your book, but they make it harder than it needs to be. All right, so just looking at 2 data sets, I normally have you play with this data, but step 1 is to put the data in order. So I'm going to remind you of how to do this on the calculator. You may want to do this with me, or you may want to just watch. Okay, in list 1, you'd put your data. So in order to do that, you do stat, edit. I also have notes for this on the back of your notes, so you're okay. Put your data in. If you want it to be in order, you would hit stat, sort, and then wherever your list is, so sort list 1. And now it is in order when I go back and look at it. Okay? So that's how I got this data, and that's how I got this data. I could get all this data from doing stat, calculate, 1 variable stats, my data's in list 1, I don't have a frequency list, and I'm going to hit calculate. Well, there's my mean, 16.75. Okay, sum of x, that's just all the numbers added up, so 201. See, if you add up all the numbers, that's 201. There were 12 numbers. Sample standard deviation, population standard deviation. And then here's your mean, median, mode, min, max, quartile 1, quartile 3, all of that. Okay, so that's how you get it out of your calculator. We know this from last semester. So I just want to go over it. Okay, I have 2 sets of data. This data had 12 data sets. If I add up all the numbers and divide it by 12, I had an average of 16.75. If you look at your notes from the book, it says round the mean to 1 more decimal point than the raw data. That's just convenient. So if it was, the raw data was 2 decimals or 2 place values, then we'd round it to 16.8. And that's just what this book likes us to do. Okay? The sample mean is the same thing as the mean, but what if instead I just randomly picked 3 of the numbers out of the data set and then took the average? That would be the sample mean. The median is 17. If I put these numbers in order, the middle would be right here, right in the middle. Okay, well, what's in between 17 and 17? 17. the mode is 17. It's the number that shows up the most. 1, 2, 3, 4 times. Let's see how many 16s are there. 3, 2 18s. So that's why it's the mode. Okay. And if we were to graph this, if these were the ages, like pretend these were your ages in class, it would be fairly symmetric. It would look like this, centered around 17. Okay, so now I took our ages, and then maybe I added my age. Okay, this is kind of old, but close enough. So at the time that I did this, I was 36. So now, how many data points are there? There are 13. So it changes a couple of things. Because there are odd data points, now instead of having the middle, the median be right in the middle, it's actually going to be this number right here. That's my median. Okay. We need to talk about quartiles, and they're going to show up down here, but I'll just show you. I'll talk about it right here. Quartiles are then cutting the remaining amount in half. So 1, 1, 1, 1. So the top quartile would be here, and the bottom quartile would be here. Okay, similarly, if we did it down there, and I'll show you later. Okay, notice that my means change. My first mean of 16.8 was representative of the ages in the class. Now the mean is 18.22. That's not that representative. Only 2 people in the class have that age or higher, because my age skewed it to the right. Okay, so it became skewed data. The median and the mode stayed the same. They are resistant to my old age being in there. But the mean was not resistant. It got pulled up by my outlier. Okay, and if you were to graph it, it would now be skewed right, because most of the data would be here, but then my outlier, here's our median, but our mean got moved up a little bit because I'm old. Any questions on that? All right, okay. A numerical summary then is said to be resistant if extreme values, very large or very small, do not seem to affect it substantially. So the mode didn't really change, the median didn't really change, but the mean did, okay? And it just shows you what happens. If they're symmetric, the mean and the median are about at the same spot. If it's skewed to the right, then the mean gets pulled right. If it's skewed to the left, then the mean gets pulled left. Okay, very occasionally, this is actually some discrete data, okay, and it's the number of adults in a household. It is skewed right. So we would assume that the mean would be to the right of the median. But sometimes with discrete data, if you have a lot of values here, even if you just have 1 or 2 outliers, your mean could still end up to the left of the mode and the median. It's just saying occasionally these pictures right here, for certain discrete data, it doesn't hold true. Occasionally, it's not enough of a pull to move up the median. Measures of center, right? So let's see. Determine the average from raw data. Find the median, the middle number. Okay. Explain what it means for a statistic to be resistant. The value doesn't change if you put in some high values or some low values. Okay, mode is the one that shows up the most. Now we need to talk about measures of spread. We talked about measures of center. Now we need to talk about measures of spread. So here's that data again in order, okay? Let's look at the mean and the standard deviation. Basically, I've got all the data here. The range is the max minus the min. So 19 minus 15 is 4. That is a measure of spread. When I did the max minus the min with the data set that added my age, notice it changed a lot. So it is not a resistant measure. Okay, the IQR though, that's the middle 50%, is 1.5, and it's 2 if you add my age. That one is resistant. It changed, but not a lot. Okay. Now, standard deviation is another measure of spread, and we've talked about this last semester. We have two formulas for standard deviation. It is every value minus the average squared, added up, next value minus the average squared, all of those added up, divided by the total population. And then you take the square root of that. Okay, so here's the formula for population standard deviation. If you're talking about a sample, you would do the same thing, but you wouldn't divide by the total value. You would divide by n minus 1. And the reason for that is it'll make your standard deviation bigger. Let's say I only had 8 people in my population, and every value minus the average squared added up was 100. 100 divided by 8 is 12.5. If I wanted the standard deviation, then I'd take the square root of that. If instead it was a sample, 8 wasn't my whole population, it was a sample, I would do the same thing, but I would divide by 7. One smaller number. And the reason that is if you divide by a smaller number, your answer will be bigger, so you're going to get a larger standard deviation to account for error. Okay, so n minus 1 makes the sample standard deviation bigger to account for more variability. Okay, this formula down here is called the conceptual formula. Basically, the only thing that's nice about this formula right here is that if you had to do this by hand, it might be easier using this formula. Okay, so on your homework, they ask you to do it one way and then the other way, and you're supposed to get the same answer each time. Just try it to see if you can use all the formulas. It's saying that you could square all the values and add them up, minus adding up all the values and then squaring them, and then dividing by the total. So this value right here, it would be taking all of these values, squaring them and adding them up. So 15 squared plus 15 squared plus 16 squared plus 16 squared. Luckily, when you do stat calculate one variable stats, it actually does that for you. So the sum of all the values squared and added up is right there. And then it says this right here, this is just all the values added up. So if I was using this formula for this data, 3,000 3,383 would be this value. This value would be 201. This value would be 12. And then this would be 12 minus 1 or 11. And I would just type it right into my calculator. It just claims that if you use this formula, you could also get the standard deviation. So let's try it real quick. 3,083 minus 201 squared divided by 12 divided by 11, and we got 1.12, right? 1.21. And if you look back at what we did when we did this, oh look, my sample standard deviation is 1.21. So it's just saying it's an alternate way to solve it that might be easier to do if you were doing by hand. So that's all this formula is. I'd never even seen it before, but the book wants you to know that it exists. So there you go. Any questions on that? Now that's how you would do it for the sample. You would just divide it by n again if you wanted it for the population. All right. And then the variance is just the standard deviation squared. So whatever comes out of these formulas, squared. So if you look at this data then, okay, this is how you solve for, this would be your population standard deviation. This would be your sample standard deviation, or sorry, I lied. Here's your population standard deviation just for your ages. Notice your ages don't vary very much. 15's the smallest and 19's the oldest. But if you put my age in it, this is a measure of how spread out the data is. It is not resistant. It shows that I'm old. That the lowest was 15 and all of a sudden the highest became 36. All right. And then again, if you wanted to do it with a sample, they get slightly bigger to account for error. All right. And then we talked about the empirical rule last time. 68, 95, 99.7, right? If data is normal, it falls in this pattern, right? Plus or minus 1 standard deviation is 68%, plus or minus 2 is 95, plus or minus 3 is 99.7. That's how we can tell if something's not just symmetric, it is normal, okay? Let's look at this. Here it says, determine the percentage of students who have IQ scores within 3 standard deviations of the mean according to the empirical rule. And what it is this is an example out of your book, and it's IQ scores out of University A, and here they are projected and presented in a histogram. The average IQ score out of this group of people is 100. They sampled 100 kids, and the sample standard deviation is 16.1, right? Because there's more than 100 kids at a university, so it's a sample. Notice they're going to claim that it looks fairly normal. It doesn't look perfectly normal to me, but it depends on the histogram. So they're saying if it's normal, then how many kids would fall within 33 standard deviations? 99.7. If it's normal, how many would be within 2? 95. Then it says determine the actual percentage of students that have IQ scores between 67.8 and 132.2. This is where those values came from. Okay, draw this on your, or sorry, it should be on there. Average is 100. Standard deviation is 16.1. So 1 standard deviation plus 16.1 plus 16.1 minus 16.1 minus 16.1 minus 16.1. That is what your curve would look like if this data is normal, right? So it says if it's within 2 standard deviations, it should be 95%. So what it asks for C is it says, look at the raw data and calculate it. Well, if I looked at the raw data, it turns out that it's 96%, not 95. I didn't give you the raw data, but if I looked at the raw data and added up the IQ scores between 67.8 and 132.2, that's 96 students. So it's not quite perfectly normal, but it's pretty good. Any questions with that? We'd expect it to be 95 if it's normal. In the real world, we got 96. Yeah, it's still pretty close to normal, okay? Then it says, according to the empirical rule, What percentage of students have IQ scores above 132.2? Well, if we go back here, 132.2 is 2 standard deviations above. Okay, so that's about 2.5% left. That's this part plus this part. And think about it, between here and here is 95, which means there must be 2.5% here and 2.5% here because it has to add up to 100. It's what we did last semester when we added up this piece and this piece. All right, so that's all review. Here's the last thing that's new. This is what happens if the data is symmetric and normal, okay? This guy's inequality works for any shape distribution, which means it's not as accurate as the empirical rule, okay? So if we want to estimate how many people are within so many standard deviations, if we don't know that it's normal, we could use this guy's thing, and it says this. For any data set or distribution, at least 1 minus 1 over k squared times 100% of the observations lie within k standard deviations of the mean. Blah, 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 blah. What? Let's look at what it's saying. Okay, it says, determine the minimum percentage of students who have IQ scores within 3 standard deviations of the mean according to this inequality. Okay, to this Russian guy inequality. And I have to look up how to pronounce his name again. If it was normal, we'd say at least 99.7% of the students fall between an IQ of 51 up to 48. 1, 2, 3 standard deviations on either side. But this guy's way of doing it is a little more conservative. So it says to do this. Okay, it says 1 minus 1 over k squared. We want to know the percent if we're 3 standard deviations away, so then k is 3. So I just put a 3 into this formula, and you would get 88.9%. This percent is just kind of built in. I don't know why they do that there. It's not really timesing by 100%. We're saying 1 minus 1 divided by 3 squared. The 3 comes from the question, 3 standard deviations away. It's saying it's going to be this percent, but we need to times it by a percent, so we times it by 100. According to this guy's calculation, it's at least 88.9% of the population. They're not going to be assured that it's 99% of the population because this is a conservative estimate. We don't actually know the shape. Okay? If you wanted it for 2 standard deviations, you just plug it in 2. So we'd say we assume 75% of the population will be within plus or minus 2 standard deviations. Okay? And the actual data had 96%. So this guy's value tends to be low, but that's okay because he's just giving you an estimate. All this is just another way to estimate how much of the population should be this far away from average. Okay, that's the whole thing.